Now you have a task to solve. Perhaps was it a man or a woman crossing the street, and man was at the beginning of the sentence. Now you go one time step back and look up, was it man or woman? And then you go the next time step, but now the contribution becomes smaller by a constant factor. Perhaps the first time you go back, it's 0.9 times the thing. Then it's again 0.9. 0.9 times 0.9 times 0.9 goes to 0. Then you say, if you encounter the word man, the contribution is 0. You cannot see it. You do not recognize the man. Meaning, if you go back in time, the contribution gets less and less and less. And that was the problem. Ideally, the contribution would be the same. No matter whether the word is at the beginning of the sequence or at the end of the sequence, it might contribute equal to the answer. And that was the idea. First, I discovered the vanishing gradient. But then the idea came of the long short-term memory. Here the idea was, can I build something, construct some architecture? If you go back in time, it's scaling with a factor of 1. My name is Sepp Hochreiter. I'm leading the Institute for Machine Learning in Linz. I'm a university professor, and also I founded a company called NXAI, which is dedicated to industrial AI. I'm very well known in this community because I invented LSTM, which stands for long short-term memory. And I did this in my diploma thesis, where my supervisor there, it was Jürgen Schmidhuber, said, yes, these recurrent neural networks do not work. I cannot store something. They only can memorize the last words. If you say, a man in a red shirt crosses the street, perhaps you only memorize crosses the street. But if you say, the street is crossed by a man in a red shirt, then you know it's the man. In speech, you can permute the words and it's the same meaning. Therefore, memorizing is important. It's also important for time series and so on. At this time, it was 1991, a recurrent neural network couldn't memorize. And then I was digging into the problem, and what I discovered was a problem which is now known as a vanishing gradient. The vanishing gradient was also the reason why deep neural networks were not possible. Because what I discovered, the gradient, which you need for doing learning, vanishes if you go back in time, and therefore you cannot see what happens at the beginning of a sequence. The same if you go through layers of a neural network, also here the gradient vanishes, and you have the same problem. Therefore, neither recurrent neural network were possible, nor deep networks were possible. And this was the problem of the vanishing gradient.
I see. Can you explain vanishing gradient a little more for listeners who are not mathematicians or statisticians?
Yeah, it's a kind of credit assignment. Now you have a task to solve. Perhaps in my previous example, was it a man or a woman crossing the street? And man was at the beginning of the sentence. Now you go one time step back and look up, was it man or woman? And then you go the next time step, but now the contribution becomes smaller by a constant factor. Perhaps the first time you go back, it's 0.9 times the thing. Then it's again 0.9. 0.9 times 0.9 times 0.9 goes to 0. Then you say, if you encounter the word man, the contribution is 0. You cannot see it. You do not recognize the man. Meaning, if you go back in time, the contribution gets less and less and less. And that was the problem. Ideally, the contribution would be the same. No matter whether the word is at the beginning of the sequence or at the end of the sequence, it might contribute equal to the answer. And that was the idea. First, I discovered the vanishing gradient, but then the idea came of the long short-term memory. Here the idea was, can I build something, construct some architecture? if you go back in time, it's scaling with a factor of 1, meaning it's equally important. If you go one step back, it's equally important. You go another time step back, it's equally important. And this was a LSTM architecture. It's called the memory cell. The memory cell was a construction where you can go back over time, and the credit assignment, how much something contributes to the final answer, remains the same. And I built an architecture around this idea, around the memory cell, which is called LSTM. And now it was possible to store information over hundreds or thousands of time steps. It was not possible before. And then LSTM was used in many different applications. It was used at some point in every cell phone, in every Android cell phone, in every Apple cell phone. It was used in Alexa. It was used by Baidu and Alibaba. Everywhere were LSTMs for language, for speech and language. And the first large language models were LSTM models. Today we heard a talk, the Test of Time Award, and this was Ilya Sutskever, one of the founders of OpenAI, got it, where he used an LSTM for sequence-to-sequence learning, which is actually translating. LSTM were everywhere, and Google was at this point known as an LSTM company.
Yeah. Can I just ask on vanishing gradient, and I'll edit this, so don't worry, because I'm a journalist, not a machine learning guy. Is that related to gradient descent?
Yes.
So gradient descent, you're working step by step to find an optimal, right?
Exactly. But it's gradient descent. It's the gradient. You want to compute the gradient to do gradient descent.
Right.
But what turns out is that the gradient is super tiny.
Yeah.
And if you have a tiny gradient descent does not work anymore, because the direction cannot be determined, because it's so tiny number. So your gradient is too small to do gradient descent. Therefore, gradient descent does not work anymore.
Yeah, I see. And so LSTM was really the original working neural network, right?
There was, especially for sequences, for speech, language, there was only LSTM. Everybody used LSTM. All big companies, Amazon, Microsoft, Apple, everybody used LSTMs. In every cell phone, an LSTM was.
Yeah, and what fascinated me about your talk is that you've continued working on LSTM. And in AI, there are these ideas that are the primary focus for a period of time, and then another strategy, another algorithm, another architecture comes along, and that becomes the focus. But it doesn't mean, I mean, that's what I talked to Isabel Giel about. It doesn't mean the support vector machines are useless. And there's still things that can can be done on them. The same with Boltzmann machines ultimately led to deep networks. But can you talk about continuing that research, and how frustrating is it to have the community then turn their attention elsewhere?
Yes, to this 2017. There was a paper, it's called Attention is All You Need.
Yes.
The idea of attention was there, but attention was always used together with LSTMs. You have attention mechanism and LSTM. And there was this paper that said we can do only attention looking back in time without an LSTM.
Yeah.
And doing this, they could parallelize the whole thing much better. They can push much more data into to the learning algorithm. They can use larger models, and then and this architecture with attention is called transformer. The transformer technology replaced LSTM, but LSTM were still used. For example, OpenAI had this DOTA 5 agent, reinforcement agent, and it was a big LSTM network. DeepMind has the StarCraft Alpha Star network. It was an LSTM network. And this year, in a Nature paper, a method come out to predict floodings or droughts. And this is based on an LSTM network. And it's done by Google. Google, you can have a Google app and you can look up, is your home in danger of floodings? Do you have to take precautions? Or is everything okay? And even the US government and the Canadian government, the official method now is this LSTM networks to predict floodings or droughts. Therefore, the LSTM network still worked, but where they were not used was in language, was for the large language models. And we saw LSTM is a very, very good technology. It excels everywhere, but not in language. But the main reason was the data. You could not push enough data. And for XLSTM, that's a revival of the LSTM in language, we looked at, can we do the same as with the transformer technology? Can we scale it up? Can we build a very big network? And what are some limitations of LSTM? And we identified 3 limitations. One was it could not revise storage decisions. If I store something, I cannot later say, oh, no, it was not correct. I want to store something else. This we did with a technique which we call exponential gating. The second thing is we built a huge memory. LSTM had only a very tiny memory. Only one number was stored. And we extended the memory. And now the funny thing comes, the memory is a Hopfield network. Perhaps you're aware, there was this thing which is called Nobel Prize. And John Hopfield got the Nobel Prize for his classical Hopfield networks. And we use internally in this XLSTM a classical Hopfield network because it's very fast and very efficient, but equipped with LSTM things like input gate, output gate. We merged Hopfield network and LSTMs to get an XLSTM. And now it has much more memory. And the third thing was to make it parallelizable, like the transformer. With these 3 ingredients, exponential gating, having a good, efficient memory, and making it parallelizable, we saw we can be as good as transformer in, for example, the 7 billion model regime. But we have a big advantage. Our advantage is we are much cheaper in terms of energy or in compute. And we are faster because we don't have to compute so much. We are also faster. We are faster and more energy efficient, both in training, but especially in inference. If you use it, if a user is using it, we can accommodate more users at the same time, or we can have one user, but with much less compute, with much less energy. And this is a huge advantage of this new technology compared to the existing technology, which is a transformer. But what I also have to say for XLSTM, language is not our prime target. Our prime target is using this technology because it's so powerful to go into industrial applications, because language is not at the core of many companies. It's nice for customer relations or PR or stuff like this. But with XLSTM, which is so fast, we can go in robotics. Transformer cannot go in robotics, or so I tried, but they were not fast enough. We have 2 advantages. We are fast enough to go in robotics, and we can fix the memory because we have a fixed memory compared in contrast to transformers. And with this fixed memory, we can adapt it to the hardware which is available, which is a smaller hardware on robots. And therefore, we can go to robotics, to embedded system like drones, to embedded system like autonomous production systems. And here we know at the core of some industries. Here we in the core at some businesses of companies. And here we see a huge advantage because we a priori know how large the memory is, and we can go to the embedded system on the machine, and we are fast enough to do it real time, so that we can really control a robot or autonomous thing in real time.
Is it a light enough in XLSTM model? Could it be light enough to have on the edge?
That's where we want to go. The guys from Apple asked us and so on. We have to look into it. What are the requirements? I think yes. If something can do it, then it should be XLSTM because it's memory efficient. Also, the energy efficiency, if you have it on your cell phone or on the edge, you don't have these huge batteries with you. And if it's more energy efficient, it's also super helpful to use it. And therefore, I think that would be a main target for this kind of models, because also look at the self-driving cars. You cannot have these big batteries. We are in contact with some car companies that would be an ideal system for us to have it in the car, because we don't have so much energy in the car because we have only a battery, and we should work in real time. We should react very fast. Both we can accommodate, both we can do. And I'm super optimistic that we have a super cool thing here.
Yeah. Going back to attention. So attention existed, and forgive me because I don't know this history. Where did attention come from? Who developed that?
So Transformer was 2007. Attention is all you need, but the attention idea, it was always in combination with LSTMs. There were different developments. There were something like, let's have an external memory where you access the memory. Also, Alex Grave had an idea which was called the neural Turing machine on LSTM, which Turing machine. And from this direction, there was then this hard attention. I store something, and I really get an address to what I should attend to. This was Jason Weston said this memory networks. The idea was memory networks. It was always, can I store some information? LSTM has something in its memory, but at this time, the memory was very small. Mm-hmm. And they wanted to have a bigger memory. Now, with the XLSTM, we use the Hopfield network, but they used a separate memory mechanism in addition to LSTM to store more information from the past. And there were different ideas out, and then there were addition attentions, there were multiplicative attentions, there were different attention mechanisms. It was always, can we integrate into LSTM more powerful memory? But they didn't replace the memory cell. I started with the memory cell with this constant not vanishing gradient, constant gradient going back. So I didn't touch it because I don't want to destroy that. But you can build a memory directly into LSTM. This is what we did. The others did a separate memory. Their attention came. And then they saw the separate memory is powerful enough, and we don't need the LSTM anymore. And this was 2017. Attention is all you need. But in 2015, the first attention ideas were already out.
I see. And so the XLSTM, where you have an LSTM and a Hopfield network to expand the memory, and it's faster. How is it trained when you say a 7 billion parameter model? Is it trained in the same way that a large language model is trained?
It's exactly the same. Yeah. We use the same backbone. And where the attention mechanism was located, we now replaced this with an LSTM. But with an LSTM with a huge memory, exponential gating, and with the possibility to parallelize it. And we did the same. We looked what did the transformer guys are doing. How do they train their networks? We did the same. We have to do some adjustments because we have a specific architecture. But the major thing came from the attention backbone, which is a ResNet. we only replaced in the big network this one item, which is quadratic in context length, ours is linear, and we are much faster by replacing this compute intensive part by a less compute intensive part.
When did you do this work? Is this very recent?
It's very recent. As attention came up, as I saw it, I thought, oh, probably we can do the same with LSTMs, but the development with transformer attention was so fast that we never had the chance to do something. And then the problem was the models became so large that we at the university did not have the compute. Then I looked at some developments and sit down, computed everything through with this Hopfield networks, with this idea. And then I went to the press and said, I have a new idea, XLSTM. I need money to try it out. And then after a while, there was a local private money, I think, which gave us money. And we founded the company, the NXAI company was founded to build the XLSTM. And the first months, we invested 10 million euros only in compute to see whether this XLSTM works. I cannot do this at the university. I needed private money.
Yeah.
And it worked very well. Then we said, let's build a larger model. Let's go to the 7 billion model. And it worked better than I dreamed. It is so fantastic.
Wow.
And I'm so proud. I had the first LSTM where all the big companies have used it, but I never saw any cent, nothing. Now I have the second chance with XLSTM, but in the company we have the IP rights and stuff like this. We try to use it on our own and bring it to industry. But it is so fantastic that it's really working like a dream.
Yeah, that's amazing. And you say it's not particularly, it's not built for language, but can it handle language?
Yes, it's as good as these language models like, Llama 2, Llama 3. It's better in performance. Yeah. But it's also much faster. It's more energy efficient. But in the meantime, there are better models than Llama. It's in the middle field of these language models.
Yeah.
But language, there are so many models out, so many things. I see the big chance to go in industrialization, to have a very fast, real-time method, energy efficient, to really to go to the core business. Because with language, you often not as a core business, you don't make the big money.
Yeah. And so give me a use case, an industrial use case for XLSTM.
What was already done, not by me, by others, some implemented XLSTM in controlling drones. And it worked fantastic. As I said, it worked better than the transformer. It worked better than state space model. It worked for them very good. It was not my idea, so I tried it out. Others used it for time series prediction. This was weather or even financial time series. And they reported it in a paper, they published it, that they're much better than transformer, much better than classical time series method. And this was another, I'm very proud, another reinforcement of that this method really works well. And there are on arXiv a couple of papers as they tried it out, and they always get new state-of-the-art, new good results. And now I hope it's getting more and more popular. More people are using it and see the power of this new method. I'm so excited.
Sure. Yeah, I can imagine. It's particularly since you had this huge success, and then Transformers kind of eclipsed it, and now you're coming back. Yeah. Is it open source, or how are you approaching that?
We made everything open source, meaning the model is open source. The inference code is open source that you can use the model, but also the training code is open source. Everything is open source. And now the funny thing comes, or not the funny thing, also we are very proud. We are faster than flash attention. I don't know whether you know flash attention is a very fast transformer technique. And it turned out that we are faster. And being faster is because we have this recurrent neural network. We have an LSTM. What we did is we have chunks of flash attention. And if you can decide how large the chunks are, you can better make use of the GPU, of the graphic processing unit, of the chip. If you have to do everything in one big flash attention thing, you have to squeeze it in. You cannot do the optimizing. But we have more smaller chunks and can optimize the chunks for the GPU. And now we are faster than flash attention because everybody thought, I told before, a transformer become popular because they could be paralyzed and they're faster. Hey, and now we are faster. We are faster than the fastest transformer. It's unbelievable. I never thought this is possible. But we achieved it. We really achieved it.
Yeah. On the drone example, is this model on the drone or is it communicating with the drone remotely? And what exactly is the model doing? Is it guiding the drone? Is it guiding it through obstacles? Or can you talk about that application?
I'm not a part of the team. This is somebody else. I was only told, as far as I know, but I can be wrong. It's on the drone, on the device, on the drone, and it's guiding the drone, it's controlling the drone without external. They have probably a remote for safety reasons,
sure.
But the idea is the whole system is on the drone, that you have an autonomous system. But it's a different lab. They did not publish this until now. They only told me they were very successful, and that's the only information I have.
Yeah. And so NXAI, is that how you're pronouncing it, or do you call it NXAI? Or
we are not sure. Until now, we call it NXAI. Elon Musk has something which is called XAI. Perhaps we should call it next XAI or new XAI. I don't know.
Yeah.
But right now it's NXAI. That's a company dedicated to industrialization of AI. It started with this XLSTM. We needed money to show that's a cool technique. And as I told, it really worked out more than I ever dreamed. But we have a second pillar. We have a second thing, and that's AI for simulation. It's also in the company. AI for simulation is you have these numerical simulations. You have many particles, or you have a mesh over your car where the air is flowing. And these numerical simulations are restricted. If the number of particles goes into millions or hundreds of millions, so numerics becomes too complicated. You have to do too many computations. But AI can be faster, can be 1,000 times faster, can be 100,000 times faster, because AI can see metastructures. I give you an example. The moon is circling the Earth. The moon has many particles and so on, but we describe the moon by its location, by its impulse, perhaps its mass, only few parameters. And we have a very good prediction where the moon is tomorrow in an hour. And this is a very high abstraction. And many physical systems have, let's say, a set of particles which form one structure, like quills or other structures. And AI recognizes the structure. Or only think you throw a snowball. You don't have to simulate every snowflake, but the ball. And if the AI recognize, hey, this is a snowball, let's simulate the whole ball as one. then you're much faster because 100,000 particles, 1 million particles are now one thing. And the idea in simulation is AI recognizes macrostructures, simulates these macrostructures, and it's much faster, but has almost the same precision as a numerical simulation, which goes down to perhaps atoms. And this AI for simulation is super important. You can do it for the food industry if you store something like in a hopper in some compartments, how it's flowing out. You can do it if you have some particles and you blow air into it to mix different kind of particles. You can see how is the mixing, are they mixed good? Even if the particles have different sizes, different structure, and all kind of things, you need the simulations. In Linz, we have a big steel industry. For this big ovens of the steel industry, the simulations, the numerical simulations are not sufficient because there are so many particles, there are so many atoms to simulate that it doesn't work anymore. But AI can do. And here we see with the simulation a huge field in industry, at the companies where we can do simulations, where numerical simulations struggle, where numerical simulations are not fast enough anymore. Yeah. That's the second thing. XLSTM, it's a new technology. It can be used for everything. And simulation using AI. These are the two main pillars we have in the new company, NXAI, dedicated to industrial AI.
Yeah. I had a conversation with Ilya Sutskever on the podcast, and he was saying that the transformer scaled very well, but it could have been anything that scaled well. He was saying that they worked with the transformer because it did what they needed to do, but he felt that it could have been a different core algorithm.
Yes.
Is that what you're finding with LSTM?
Exactly. Yeah. At the beginning, had the same feeling. There's a tension at the core, or an LSTM or something else. It's the scaling up, building a very huge network, storing all the information in the weights, in the connections. I think that's the important thing to build up a big network. They use transformer. The only disadvantage now of the transformer is everything else would perhaps also have worked. It's quadratic in the context length. They used a little bit more complex thing, and it's complex in time, but it's simple in the interaction because you have a query and you have keys. Every query looks at one key. You have only pairwise interactions. With LSTM, you have everything in a memory, and a new query interacts with the whole memory. Therefore, you can have also more complex, more abstract interactions. But I decided for this. I think others also go. But now, if you look in detail, perhaps it's better to have something more compute efficient, something which does not need so many resources in terms of computational cycles.
Yeah. And so you've scaled this so far to 7 billion.
Exactly.
But there's no reason, if it's faster and more compute efficient, presumably could you scale it beyond what they've done with LLMs?
Yes, I think so, that we can do it. We have to see whether we have enough money, enough compute to do that, because we are looking for investors and so on. We need money to do that. But I think we're in a good place because we are now faster. We can do even larger models. But the question is, how large should the model be? Also, Ilya today said, perhaps it has an answer scaling. Yeah. I also in my talk said there was a scaling. There's no more data available. We used all the language data up, and producing with existing methods a new language data also doesn't work because it's not new information. It's old information. Old language only transformed. Also, we don't have new data. And here I think we are saturating because we used up all language data we have, also from Chinese, Japanese, across the world. This was all translated. If we want to build larger models, but we need also more data. But the data is, I think, is a limitation. We don't have more data. And I think this is an answer scaling. Now we have to think more in inference. And OpenAI has this strawberry model where you should think more, or what I think it's more, there's information in the model, but you have to get access to it. You have to tweak the model a little bit to get out what you want to have. And that's an inference. And now, the cool thing is, XLSTM is fast in inference. Exactly here we have an advantage. We can do much more. If the transformer can do 100 tokens, we can do 10,000 tokens in the same time. And here for inference, also we would have an advantage. And therefore, I'm very hopeful, perhaps still being in language. I said we want to go to industrial application, but language is interesting after the O1, after the strawberry of OpenAI. I'm super hopeful that we have a system which can think much faster. And also this is a direction I want to look into.
Do you think that that XLSTM has promised to challenge the large language model paradigm, where in a few years we'll be talking about XLSTM models instead of large language models?
Depends. I don't know how everything has worked, because this existing technology is very good integrated in the systems, in the hardware. Nobody wants to change a working system. But if I say you save a lot of money because you need less compute, I don't know whether we are too late to change, because everybody bought already their language models, and had their product on the market. I don't know. But I think there are certain fields we have an advantage. But whether we can change things which are already fixed, I don't know. But in principle, it would be possible. You have a model. It's a GPT. It's a transformer model. Now you replace it by an XLSTM. And you have the same performance, but pay less energy costs. But I don't know. It's a market thing, and
sure. On the training data, I heard Jan LeCun speak yesterday, and he was talking about this problem and how we need to develop methods to collect data from the real world.
Yes,
not filtered through language, through various sensors, through real-time video, through haptic sensors, through I don't know what else there is, but audio, I suppose.
Yeah.
Could XLSTM handle different modalities?
Yes, absolutely. It can. And that's also with simulations where we go. With simulations, we also need data. Where comes the data from numerical simulations, which simulate the nature very precisely. Then we can generate more and more data very slowly, because so AI methods are faster, but if you wait enough, then you have enough data to build them. But also from sensors. If you want to use XLSTM in different applications, we rely on this sensor data, exactly like Jan said. I think that's the future. That's where we get new data. We don't get new data in language, but we get new data in many different applications, because we can build more and more sensors which just record what's happening in the world for a machine, how a machine is in the world. And then we can do the same as we do with languages, use like an XLSTM to build a good model. And now a model which can control a machine, can make decisions or stuff like this. Yeah. I think that's the future, yeah.
And the learning is this are these models as they do they continuously learn after the training phase, or are they then fixed?
That's your decision. You can do both, but normally what you do, you fix them, because if the user is training these models, you don't know what's happening.
Right.
It could be very risky. If you can also train a car to stop at green and drive at red, because if you're a very bad teacher to the car, and for some safety reasons, you don't want them to learn. But on the other hand, there could be machines where the machine dynamics change over time, because some parts are worn out or are not precise anymore. But then the model can adjust to the machine or adjust to the weather. Perhaps it's summer and then it becomes winter. It could have advantages, but one have to look into the application. You can let it learn, but you have to see, is it dangerous that the user is in control in learning something?
Yeah, well, I wasn't thinking about consumer facing applications, but for example, industrial robots.
Yes.
Again, Covariant, this company founded by Peter Abel, their dream is to have, and I think they already have them networked, these industrial robots deployed around the world. And as they encounter new situations and learn to deal with new situations, that learning then is sent back to a central model and then deployed to all of the robots. So it's this learning.
Yeah.
Is that something that could happen with XLSTM?
Yes, XLSTM can do that, but it can do it even better. Right now, with robotics, you cannot learn on the robot because these systems are too big, too clumsy.
Right.
But with XLSTM, you can do it embedded. You can build it on the robot, and an individual robot can even learn.
Yeah.
You can use the data, pull it, and learn a new big system. But with XLSTM, it would be possible that each robot learns, adapts to its own environment, to its own task. And that's the thing. What we have in mind, for example, is if you have the industrial robots, you have almost 100,000 millions of items to build. But for many smaller companies, you have only perhaps 500 products or 700. Now it's not you don't program a robot because it doesn't pay off to program a robot. If you have a robot which can learn, perhaps you show the robot you have to do this, screw in here, do this, do this. You show it on 2 or 3 examples, and the robot does the other 700 examples. Here, XLSTM would be good. It's on the robot. It's a foundation model. It knows how to screw in and do stuff. But now you have to say for this item, you have to do exactly this. There will 700 of them, and it's doing this. And that's not possible right now because industrial robot can do it, but to program it costs more than doing let human is doing. And here with XLSTM, we can put it on the robot, and therefore it can learn more in context, because you would do some demonstrations from human into the context, and now with this in context, it will do a smaller piece, smaller number of pieces, and here I see also a huge potential.
Yeah. Is this deployed already on industrial robots?
No, because we come out with a language model. We first wanted to show our new technology is powerful enough.
Yeah.
Our new technology is as powerful as the existing technology, which is called transformer. Now, if we have shown this and everybody believes us, we will go in these different applications.
Right. And NXAI, when was it founded?
It was founded end of last year, December last year.
Yeah. And how much money have you raised so far?
We have internally, I cannot reveal everything, but couple of tens of million euros. But now we wanted to start a second founding round. We didn't start a round to get new investors in. We now first put out the 7B model and seeing how it's going. And now we hope money comes in to go the next step.
Yeah.
Because now we have proven we can do it. And I'm really, really optimistic that this really goes through the roof.
Yeah. Are you satisfied with the attention you're getting from the AI community on this XLSTM? I mean, I was really impressed by the talk that you gave, but I have no way of judging.
Perhaps you have a better way than me. I don't know, because I also I'm in the bubble.
Yeah.
Everybody who's coming to me say, "Hey, a cool thing," and also I used XLSTM. It's really good, but I don't see the big picture. And we have to see how many downloads we have, how many publications come out, how many other success stories are there.
Yeah.
If there are more and more and more success stories, it worked. But we have to see. I'm not sure how whether it really grows or whether it's I don't know.
Sure. Do you think that there are other algorithms out there yet to be discovered that can scale and are maybe even more efficient?
I think the field is open again. There's also the state-based models like Mamba. We compared to Mamba, we have advantages to Mamba. And the nice thing is Mamba 2, the newest version of Mamba, is an XLSTM without the exponential gating. We converge to the same architecture even. We have a little bit more performant architecture, but this was also funny because they come from this direction, we come from another direction, but we discovered the same things which work, but there could be other things out there, and also building on top of XLSTM, it's quite new. A handful of researchers have developed it. We don't know what is the potential, in what direction it can go. Everything is possible here. With the transformer, it was the same. It was discovered, published, and then many ideas from the researchers come in. And here, I think also there's a huge potential. For example, you can modify some memory. Here, for the transformers, there was something like, it's called prompt engineering. Here you can modify some memory. If you say, no, you were friendly in the past, no, you were very technical in the past, you can directly modify memory. I don't know what's in there. I know it for biological application, what I did. So learned certain proteins, put it in the memory, and took the memory to generate something else. I can take this memory, or a combination of memories. I scan over, store information in my memory, and then I pull it out. There are complete new ideas possible here.
Is there anything I haven't asked that you think I should ask?
That's I don't know what the audience is interested in. The main message came over. I hope that there's a new technique. Everybody can use it because it's open source.
Yeah.
Everybody should try it out, play around with it, and you will have a very rewarding time to check it. I don't know what's missing.
Yeah. And on the reasoning, you mentioned Strawberry or O1. Will you develop a reasoning capability, the sort of long thinking capability that OpenAI is working on?
Yes, we also think going in this direction. OpenAI did not reveal what they're really doing, but they also from DeepMind, from other research groups, some ideas out how to do the reasoning, how to do the thinking. we will also try out different things which are out there, because we see an advantage that we are so much faster in inference, and this should help us. But we will try out many things, and if OpenAI once revealed what they have done, perhaps we also build it.
Yeah. On your site, is there a public facing demo or?
Not now. I think it's because we built the 7B model,
Right.
but did not have time to fine tune it to
Sure.
to a chatbot or whatever. That's not what we had time right now.
Yeah.
We are super proud that we got this cool model.
Yeah. Okay. So we've got to watch you develop.
Yeah, please
And
do.
NXAI, what's your website? NXAI.
It's I have I don't know it out of the mind. NXAI, no, nx-ai.com.
Yeah, nx-ai.com.
Yes.
Yeah. Well, I'll follow it. Okay, this is fantastic. I'm really glad that I got you up here.